As we study the boundless universe, our gaze often meets giant galaxies, twinkling stars, and beckoning planets, and this really excites our imagination. Still, there are countless other celestial bodies hiding in the silent emptiness. With their size rather modest, their dark surface hardly reflects any sunlight. Many of these objects remain concealed from us, as they are practically invisible in telescopes. But in spite of these challenges, thousands of small objects have been discovered in the solar system so far. Satellites, planetoids, and asteroids. And today, we're going to visit some of the most unusual and fascinating ones. Our journey will start in the Asteroid Belt, the keeper of the secrets of the solar system formation for billions of years. Having made our way among debris scattered around space, we'll get to Jupiter's Galilean satellites and pay special attention to the unpredictable and dangerous object called Io. Our next stop will be Saturn and its magnificent rings. Whizzing through those, we'll descend into the foggy atmosphere of the mysterious Titan. And in the end, we'll get to the guard of the remote borders of our system, the inconspicuous and little-studied Pluto, eternally icebound. Let's get ready, and we begin. Kosmo. Today, over 300,000 small celestial bodies found here have been given names and numerical designations. Interestingly, their overall number may well reach over 1 million. The starting point of studying the asteroid belt may be defined at 1801, when astronomers spotted a mysterious object in the sky after a long and hard search for the fifth planet. In terms of its parameters, it appeared to be a planet, but happened to be so small that even the most advanced telescopes of the day couldn't distinguish its disk. The researchers saw the newly discovered object as a bright dot like a star. It was dubbed Ceres, and very soon similar celestial objects of this class were discovered. A new term had to be introduced to refer to them. These unusual astronomical bodies came to be called asteroids, which literally means star-like. Apart from asteroids, this area in the solar system contains great amounts of cosmic dust. While slowly spiraling up, its tiny particles scatter sun rays and create a very faint white glow. This glow is referred to as zodiacal light. Interestingly, in equatorial areas of the Earth, it can be seen with the naked eye. For a long time, the following hypothesis used to be widely accepted. Asteroid belt objects were thought to be debris of a destroyed planet. However, today this assumption doesn't really hold water. First of all, the mass total of all the objects of the main asteroid belt is too small and equals just 3 times 10 to the power of 21 kilograms, or 4% the mass of the Moon. Even allowing for the fact that the greater part of asteroids would have left the belt a while ago, the total mass of the rocky debris still falls short of making up an object with dimensions comparable to those of a proper planet. Secondly, estimates show that large celestial objects cannot form in this area of the solar system on account of Jupiter's gravitational influence. Mathematical modeling revealed that the largest formations in the asteroid belt have never measured over 1,000 kilometers in diameter. The gravitational influence of their mighty giant neighbor rendered their orbits highly unstable, which made potential protoplanets collide and disintegrate into smaller bits. Traces of these collisions can still be observed. Most objects of the main belt group together to form the so-called asteroid families, populations of asteroids of similar makeup and of the same origin. It is thought that they formed as a result of such destructive collisions. The borders of the main asteroid belt are rather blurred. Most of the objects making it up lie within 2.06 to 3.27 astronomical units from the Sun. These boundaries are predefined by Jupiter's tidal forces and are referred to as Kirkwood gaps. Any celestial objects getting into these zones experience the massive gas giant's strong gravitational influence, which destabilizes their orbits. This is the reason why the space object count here is considerably lower than beyond. Kirkwood gaps can be found not only on the conventional borders of the belt, but inside it too. Two of the most clearly defined gaps lie 2.5 and 2.82 astronomical units away from the Sun. The asteroid belt is also conventionally divided into two large areas, inner and outer belt. The border between them is a Kirkwood gap with a radius measuring 2.5 astronomical units, which coincides with the highest orbital resonance with Jupiter. It's in the outer part of the main belt that the largest object in this area of the solar system is situated, Ceres. This celestial object used to be thought a planet, then an asteroid, but eventually, in 2006, it was given the status of a dwarf planet. It was possible to do so thanks to the fact that Ceres has a spherical shape, unlike the absolute majority of the other objects in the belt. Its diameter measures around 940 kilometers and its mass 9.4 times 10 to the power of 20 kilograms, which incidentally accounts for around a third of the overall mass of the asteroid belt. This makes Ceres approximately 6,000 times lighter than our planet. The furthest point of the dwarf planet's orbit from the Sun is 2.9 astronomical units. When Ceres is at its perihelion, the distance to our system's center measures around 2.5 astronomical units. At this point, the planetoid's surface temperature may reach 239 Kelvin or 33 degrees Celsius below zero, although its average temperature is noticeably smaller, at just 167 Kelvin or 106 degrees Celsius below zero. The celestial body is thought to be made up of a rocky core enveloped in a cryomantle around 100 kilometers thick. Water ice accounts for up to a half of the dwarf planet's volume, or 20 to 30% of its mass. The inner part of the belt harbors the largest and most massive known asteroid in the solar system, Vesta. The object's average diameter measures roughly 525 kilometers, and its mass is around 2.6 times 10 to the power of 20 kilograms, which is almost 4 times as little as that of Ceres. The asteroid's orbit is rather elongated, with its aphelion 2.57 astronomical units and its perihelion around 2.15 astronomical units away. It takes the celestial body 3.6 Earth years to complete a full orbit around the Sun. Vesta is also remarkable for being the only asteroid visible to the naked eye. It can be seen not only on account of its impressive dimensions, but also thanks to its comparatively light surface that reflects about 42% of light shed on it. Besides, the minimal distance between Vesta and the Earth isn't that great, at just 177 million kilometers or 1.18 astronomical units. It is assumed that Vesta is a fully fledged planet in terms of its inner makeup. It appears to have a metallic core made up of nickel and iron, as well as a rocky mantle. The surface temperature of the asteroid is currently fluctuating between -190 and -20 degrees Celsius, but it used to be much warmer in the past. Dark areas to be seen on the surface in the Western Hemisphere are highly likely to be basalt plains. Such terrain features may have formed as a result of volcanic activity or collision events with massive astronomical bodies. The most outstanding geological feature on the asteroid is the giant impact crater referred to as Rhea Silvia, whose diameter measures up to 500 kilometers, and its depth is around 25,000 meters. The second largest mountain in the solar system is situated at its center, towering higher than 22 kilometers. Impressively, the crater's diameter almost equals Vesta's size. It looks like the asteroid collided with a really large object at some point in the past. The collision would have produced not only the Rhea Silvia crater, but also a great number of small bits, which are now classified as the family of Vesta's numerous asteroids. The family counts over 15,000 objects. making up around 5% of all celestial bodies of the main belt known to science today. It is posited that most asteroid families came to be as a result of destructive collisions of two large celestial objects. Sometimes the debris are mutually attracted by gravity forces, which usually blend them into a new astronomical object. However, it would have lost its monolithic nature, and sometimes astronomers informally call such formations rubble piles. For example, Sylvia, one of the largest objects in the asteroid belt, seems to fall into this category of celestial bodies. Its parameters are 384 by 262 by 232 kilometers, with a mass 1.5 times 10 to the power of 19 kilograms. This makes the asteroid's average density just 20% higher than that of water. Estimates show that cavities may account for 25 to 60% of its volume. It takes Sylvia 6.5 years to complete a full orbit around the Sun. The object's orbit's furthest point from the center of the system is up to 3.7 astronomical units. In its perihelion, Sylvia gets as close to the Sun as 3.2 astronomical units. It is assumed that some bits of debris left after a collision are not attracted to other bits, but rather become satellites of the new celestial body. Sylvia is known to have two such companions: Romulus, with a diameter measuring 18 kilometers, and Remus, measuring around 7 kilometers. Their makeup hasn't been studied yet, and it is highly likely that these objects are not monolithic either. Besides, Sylvia may theoretically have smaller satellites as well, which haven't been detected yet. Pallas is another remarkable object in the asteroid belt. It was discovered back in 1802 right after Ceres, and is the second largest asteroid in the belt. The average diameter of the celestial body is around 512 kilometers, and its mass is roughly 2 times 10 to the power of 20 kilograms, which is approximately 25% less than that of Vesta. The asteroid's orbit is exceptionally elongated and tilts to the ecliptic plane at 35 degrees. That is the reason why the astronomical body is so hard to investigate with probes. As for its orbital period, it takes Pallas around 4.6 years to orbit the Sun, in the course of which the distance to the system's center changes more than 1.5 times. With its perihelion 2.1 astronomical units, its aphelion is 3.4 astronomical units away. Pallas's surface is widely pockmarked with craters, much more so than the larger Ceres or Vesta. Studies of the chemical composition of the asteroid's surface reveal that it mostly consists of silicate rocks with small amounts of iron and water. Just like Vesta, this celestial body is thought to be one of the few potential protoplanets that are still around, which means that studying it may yield important information about the formation process of the solar system. Unlike Vesta, most asteroids cannot be seen either with the naked eye or through amateur telescopes. One of these elusive objects is called Interamnia, admittedly one of the most mysterious objects of the main asteroid belt. This is an irregular-shaped asteroid with parameters 362 by 348 by 310 kilometers, and its mass accounts for roughly 1.2% of the overall mass of all objects in the belt. In spite of its relatively large size, however, Interamnia remains largely understudied. One of the difficulties thwarting scientific progress here is the asteroid's dark surface, which absorbs around 93% of light shed on it. Interamnia falls into the exceptionally rare spectral class F, which is a subclass of carbonaceous asteroids. Research of its reflection shows that the color of the celestial body's surface is even, which means that Interamnia hasn't experienced big collisions for quite a long time. Interamnia's density is not that great, at just twice that of water. The asteroid is thought to be made up of a hard rocky core enveloped in a thick layer of ice. The surface is covered with great amounts of fine dark dust. It takes Interamnia around 5 years and 4 months to complete a full orbit around the Sun. its aphelion is on the opposite side from 4 largest objects of the main belt, and the distance from the asteroid to the Sun varies from 2.5 to 3.5 astronomical units. In theory, Interamnia's orbit crosses the trajectories of such large objects as Ceres and Pallas, but estimates show that chances of their colliding with each other are small. There are millions of objects in the main belt, from dwarf planets to tiny meteoroids the size of a cobblestone. However, distances between them measure thousands upon thousands or even millions of kilometers. That is why a spacecraft crossing the belt would be running an almost negligible risk of getting hit by any astronomical body. Still, mathematical modeling shows that around once every 10 million years, some remarkable collisions take place in this part of the solar system that produce new debris. Even though a manned mission to asteroids in the main belt will not be in the pipeline for a long while, some of the asteroids there have been studied with the help of interplanetary space probes. For example, the Dawn probe carried out observations of Ceres and Vesta in the period from 2011 to 2016. Quite recently, the space probe Lucy blasted off the surface of the Earth. Even though its main goal is the so-called Jupiter Trojans, the spacecraft will approach the object known as Donald Johanson in the main belt and take its pictures in 2025. Also, the launch of the Psyche project is scheduled for July 2022, with the largest known metallic asteroid of the main belt as its target. Within the mission, the probe is planned to reach its destination by early 2026 and remain in the asteroid belt for at least 21 months while studying the asteroid's terrain, makeup, and magnetic field. For biological life to originate and start evolving, a medley of a great number of factors is called for. The chief ones are liquid water, an energy source, and a certain chemical diversity. Apart from the Earth, several more places in the solar system are potential life-harboring candidates, with Mars as the most prospective one and most closely studied starting from the recent past. Still, there are chances of discovering alien life beyond its orbit too. All it takes is to have a closer look at the next closest planet to us after Mars if we look away from the Sun. Jupiter is the largest planet in the solar system. Its mass is 318 times that of the Earth. This is a gas giant made up mostly of hydrogen and helium. Apart from these, methane, ammonia, sulfur and nitrogen compounds and water ice have been detected in its atmosphere. In spite of the diversity of chemical compounds, the possibility of finding life forms on Jupiter itself is minuscule. What with the absence of any hard surface, high temperatures of the planet's inner layers and unimaginable pressure in its interior, biological creatures simply have no chances of survival. At the same time, Jupiter boasts quite a vast array of moons. 4 of the most well-known ones, Io, Callisto, Ganymede and Europa, were discovered as far back as in 1609 by Galileo Galilei. Quite close to the Moon and Mercury in size, they are on the list of the largest satellites in the solar system. It is also suggested that Jupiter accumulated substantial amounts of thermal energy due to gravitational contraction when forming. As a result, it is now giving off more of this energy than it is getting from the Sun. That is why the gas giant, with all the objects orbiting it, may be seen as a curious version of the solar system in miniature. At first glance, Jupiter's moons may appear to have no prospects in terms of searching for extraterrestrial life. Far from the Sun, they are encased in ice, and their atmospheres are not dense. However, on closer scrutiny, these celestial objects reveal something excitingly promising. Callisto, Europa and Ganymede are highly likely to have liquid oceans under the ice shell. Estimates show that space objects with concealed oceans may offer favorable conditions for life even if they are much further from their star than planets like our Earth are from the Sun. The thick icy shell on their surface serves not only as protection against radiation and meteorite infall, but also acts as fairly good thermal isolation. That is why it is feasible that conditions inside a massive layer of water may be good enough for life to originate and evolve there. These assumptions make Jupiter's satellites some of the most attractive objects for exploration within the solar system. And now let's have a closer look at each of them. Ganymede is the largest and most massive celestial object in Jupiter's environs. Of all the satellites in the solar system, it is not only the one sporting the most impressive dimensions, but it also resembles a real planet more than any other. Ganymede's radius measures 2,634 kilometers, which is 8% more than that of Mercury. As for its mass, it equals 1.48 times 10 to the power of 23 kilograms. This is twice the mass of our Moon. Interestingly, Ganymede is the only satellite in our solar system with a liquid metal core and its own magnetosphere. Processes of nuclear decay take place in Ganymede's interior. This heats the satellite still more, with the average surface temperature 110 Kelvin or 163 degrees Celsius below zero. The core, on the other hand, is estimated to be as hot as up to 1,500–700 Kelvin. Investigations of Ganymede's magnetic field, carried out by the Galileo space probe, showed that there may be a multi-layer salty ocean under the satellite's icy shell as deep down as 200 kilometers or more. The number of layers may reach 4. Water in each is of different salinity, density and temperature, with the layers separated from each other by some ice. Spectrographic investigations of Ganymede's surface show it to have a rather rarefied oxygen atmosphere. This, however, isn't an irrefutable proof of there being biological life on the satellite. Molecular oxygen is likely to form as a result of the exposure of water ice to ultraviolet radiation. Hydrogen, the other product of this chemical reaction, floats away into space. Oxygen, meanwhile, which is a heavier element, settles close to the surface. Apart from large amounts of water ice, other elements found on Ganymede's surface are carbon dioxide, sulfur dioxide, sulfates and some other organic substances. They may well have originated in the depths of the subsurface ocean, but the mechanisms of their settling on the satellite's surface are still not clear. Callisto is another celestial object potentially just as attractive for life. This satellite is Jupiter's second largest one and lies furthest from it. Its diameter measures 4,820 kilometers, almost like that of Mercury. Callisto is encased in an icy shell as thick as 80 to 150 kilometers, and it is highly likely that there is a salty ocean concealed under it containing large amounts of ammonia and other substances. The estimates of its depth range from 50 to 300 kilometers, and its temperature is around 251 Kelvin or 21 degrees Celsius below zero according to most models. Due to impurities and high pressure, the water in the ocean should remain in its liquid state. Below the subsurface ocean there is bound to be a layer of ice as thick as around 300 kilometers, and the satellite's core, made up of water ice and rocks, lies still deeper down. Callisto's surface is pockmarked with craters. Spectral analysis of light reflected from this celestial object revealed not only water vapor and silicon rocks, but also ammonia, carbon dioxide, sulfur, iron and magnesium compounds, as well as tholins, complex organic polymers containing nitrogen. These brightly colored substances form on the surfaces of celestial bodies, a result produced by ultraviolet radiation. Callisto happens to lie too far from Jupiter to get more heat from it. Besides, the tidal influence exerted by the giant neighbor isn't enough to deform the satellite, although friction in the process would heat it up. Also, most of this body is made up of ice, whereas it is preferable that there should be solid rocks, which would saturate water with elements vital for life forms to originate. With the diversity of chemical compounds here rather modest and the temperature quite low, it hardly improves chances of life evolving here. Still, this possibility should of course not be ruled out yet. The most promising of Jupiter's satellites in terms of searching for alien life is Europa. The smallest of Jupiter's 4 Galilean moons, it is just a bit smaller than our moon. The equatorial temperature on this celestial body is 110 Kelvin or 163 degrees Celsius below zero. At the poles, temperatures may drop to 50 Kelvin or 223 degrees Celsius below zero. Europa is tidally locked to Jupiter, facing it with the same side only. However, its rotation isn't synchronized ideally. There are deviations from the calculated trajectory. This may mean that there is a liquid layer between Europa's surface and core. This assumption is confirmed by observation of interaction between the satellite and Jupiter's magnetic field carried out by the Galileo space probe in the late 20th century. Apart from that, analysis of crevices Europa's surface is covered with shows that the satellite's crust moved 80 degrees with respect to the interior. This would have been impossible without a liquid layer between them. The massive neighbor exerts a strong influence over Europa by causing powerful tidal waves in its subsurface ocean. This way, the satellite is heated still more by internal friction. Estimates show that the temperature in Europa's interior is high enough for an ocean of water to be in liquid state. Its depth may reach 100 kilometers, and its volume may be twice that of the global ocean on our Earth. Europa is covered with an even layer of exceptionally smooth and clear ice. The highest elements of relief tower just several hundred meters above the surface. The thickness of the icy crust may be anything from 10 to 30 kilometers, although the satellite's surface is streaked with a whole net of long and deep cracks. Some of them may well reach as deep as the subsurface layer of water. Thus, the ice at the bottom of these ravines is valuable material for studying the inner makeup of Europa. Another peculiar feature of this moon is powerful ice-cold vapor geysers. They open up only when Europa is at its furthest point from Jupiter, with the height of the spurts reaching as much as 200 kilometers. These giant jets are made up of water vapor, which incidentally is unexpectedly clean. It is still not known for certain whether the geysers have anything to do with the ocean in Europa's interior, or they come from gargantuan lakes embedded in the satellite's icy crust. Today, the composition of the subsurface ocean on the satellite is estimated by analyzing the ice covering the inner part of its largest craters. Only a really large object is capable of breaking the thick layer of the ice clean through on impact. After the icy crust is broken, the water in the subsurface ocean at the impact site freezes and forms the bottom of a crater. Spectral analysis of the craters reveals magnesium, sulfur and iron compounds, as well as hydrogen peroxide and strong acids. This demonstrates that there is a vast diversity of minerals in the satellite's concealed hydrosphere. Europa's atmosphere contains oxygen, which forms as a result of ultraviolet radiation interacting with the ice water on the surface, splitting the water into oxygen and hydrogen. The satellite's atmosphere, however, is approximately 1 trillion times as rarefied as that of our Earth. Still, according to some estimates, concentration of oxygen in Europa's subsurface ocean should be sufficient for supporting single-cell aerobic life forms. Underwater volcanoes should be their sources of energy and food, as they saturate water with sulfur and iron oxides. Primitive organisms may attach themselves to the bottom side of the ice crust or swim freely in water. It was even assumed that there may dwell primitive multicellular organisms in Europa's ocean. However, this hypothesis appears to be rather too presumptuous. In fact, there is a great many species on our Earth which would be able to survive in the estimated conditions of Europa's subsurface ocean. There are among them not only bacteria resistant to harsh environments, but multicellular creatures too. For example, tardigrades. Consequently, we cannot rule out the possibility of primitive life originating in the depths of this celestial object of its own accord. Unfortunately enough, in spite of the keen interest we have in Jupiter and its satellites, So far they have been investigated only briefly, and that by spacecraft passing them on their way elsewhere. No landings on the gas giant's satellites have so far been attempted. At the moment, the largest planet in our system is being investigated by the Juno probe, but as soon as in July 2021, it will move on to studying the Galilean moons. The data collected by Juno will undoubtedly be of great importance and help get to the bottom of processes taking place in Jupiter's system. As for upcoming missions, back in 2012, the European Space Agency announced starting work on the JUICE project, or Jupiter Icy Moon Explorer. The mission of the project is to explore in detail the gas giant itself, as well as Ganymede, Europa and Callisto. JUICE will be launched next year, but will reach Jupiter's environs only in 2029. The mission is scheduled until the year 2033. If all goes according to plan, our knowledge about the gas giant and its satellites will be substantially expanded. Another big research project is NASA's Europa Clipper. This automatic probe is planned to lift off the Earth's surface not later than 2023 and to reach Jupiter's system in 2032. The probe's objective is quite predictably Europa. In contrast to JUICE, it is this celestial body that Clipper is supposed to focus on more closely. More than 4 centuries ago, back in 1610, Galileo Galilei made one of the greatest astronomical discoveries of his time. Through his telescope, quite small by modern standards, he managed to make out 4 objects close to Jupiter. One of them was named Ganymede and is now considered the largest satellite in the solar system. The other 2, Europa and Callisto, have proven to be promising candidates for the search for extraterrestrial life. The 4th satellite, located closest to the gas giant, was dubbed Io. For a long time, technical limitations have prevented us from seeing details of the surface of this celestial body, and its composition and internal structure remained a matter of conjecture. However, thanks to the advancement of science, astronomers have gained more and more information over time. Today, Io is known to be one of the largest satellites in the entire solar system, second only to Ganymede, Titan and Callisto in size. Its radius is 1,821 kilometers, and its mass reaches about 8.9 times 10 to the power of 22 kilograms. If we compare this celestial body with the Moon, it turns out that these objects are almost identical in size. However, if we compare the masses, we will notice that Io is more massive than the main satellite of our planet by as much as 21%. This suggests that the average density of this space object is higher than that of any other satellite in the solar system. According to calculations, it is about 3.5 grams per cubic centimeter, which is noticeably higher than most non-metallic rocks. And to understand the reasons for the anomalous density of Io, we need to look deep into it. According to today's concepts about the structure of celestial bodies, Io has a relatively compact core at its center, made up of iron and sulfur. It accounts for about 20% of the satellite's mass, and its radius, according to different estimates, is between 350 and 900 kilometers. Calculations show that given such parameters, internal heat release will be insufficient to melt most of the core. This is also confirmed by the fact that this celestial body has almost no magnetic field of its own. Mathematical modeling shows that the satellite's core is surrounded by a solid mantle, at least 75% of which is made up of the magnesium-bearing mineral forsterite. According to calculations, its outer part is molten and forms an ocean of magma about 50 kilometers deep. Its temperature is about 1600 Kelvin, which is more than 1300 degrees Celsius. deeper layers are under high pressure, and therefore they retain a solid state even at extremely high temperatures. In its turn, the mantle is covered by the lithosphere, which is between 12 and 40 kilometers thick. Despite its considerable thickness, it is not monolithic. In some areas, the surface of the celestial body is cracked, forming large structures filled with lava. At the same time, spectral analysis shows that unlike with most satellites, there is virtually no water, ice or frozen gases on Io. The outer surface of the celestial body consists of basalt and sulfur for the most part, but also has flecks of other dense minerals. And this is exactly what accounts for its abnormally high density. By the early 21st century, Io's surface had been explored by at least 5 automated orbital stations, but it's the Pioneer and Voyager programs that provided the most key insights back in the 1970s. In the images transmitted by the probes back to Earth, scientists detected giant gas emissions, some of them reaching as high up as 500 kilometers. This observation opened a new page for scientists in the study of the solar system, because previously active volcanoes were known to exist only on Earth. For the first time, it was not frozen lava flows that had been frozen for a while, or volcanoes that went extinct billions of years ago that astronomers saw outside their home planet. They saw active eruptions, in some respects even more impressive than those on Earth. In total, about 400 active volcanoes have been found on the surface of the satellite, which is about 2.5 times fewer than on our planet. However, its area is significantly more modest than that of the Earth, which allows us to consider Io the most active volcanic object in the solar system. It is not surprising that such an unusual celestial body has attracted close attention of astronomers. During the exploration missions, a huge number of photographs of different resolutions were accumulated, thanks to which it was possible to compile a complete geological map of Io in 2012. Its quality allows us to see the largest features of the celestial body's relief, such as plains, mountain ranges, lava flows, and of course, numerous volcanoes. And one of the most notable features is certainly the huge orange-brown ring located in the southeastern part of the satellite. This vast area extends for more than 1,000 kilometers and is comparable to a large African country in terms of its size. It is believed to be formed by deposition of sulfurous emissions from the ancient Pele volcano, which is located in the center of the ring. Analysis of photographs taken both in the infrared and visible ranges shows that in the center of the ring there is the patra of this volcano, which is a multi-level cavity reaching 30 by 20 kilometers filled with lava. Incidentally, the temperature of the molten rock surface is distributed unevenly and constantly varies, reaching 1300 degrees Celsius at the hottest points. The patra is believed to be connected to the satellite's glowing mantle by an underground channel. The lava inside the rift is constantly stirring due to the fact that volatile substances dissolved in it try to rise upwards with a flow of molten rock following. Because of this, the thin crust of solidified matter covering the surface of the lake occasionally cracks and breaks, causing outbursts and lava ejections. Some of them can be upwards of 300 kilometers in height, sending solidified sulfur and rock particles straight into space. Gradually losing speed under the influence of gravity, the volcanic precipitation disperses over the surface of the satellite and then gently descends downwards. This is how the giant ring is formed, so clearly visible from space. Many of Io's volcanoes have similar formations, but the Pele ring is the largest. It is active volcanism that is the main reason for the formation of Io's special, unique atmosphere. According to available data, the atmosphere of the satellite is very thin and mainly consists of sulfur dioxide. At the same time, its density varies greatly from region to region. For example, in volcanic plumes, the gas pressure is 25 million times lower than on Earth. Away from eruptions, meanwhile, the atmospheric pressure on the day side of the celestial body is on average 1 billion times lower than the value we're accustomed to, and the night hemisphere of the satellite is almost in complete vacuum. The atmospheric density there is trillions of times lower than the Earth's. Also, despite the fact that Io's atmosphere is extremely rarefied and the satellite has no magnetic field of its own, polar lights have been observed on Io. Charged cosmic particles, accelerating in Jupiter's magnetosphere, bombard the nearby satellite, causing a multicolored glow in its atmosphere. Interestingly, Io's auroras, unlike those on Earth, most often occur at the equator, as it is there that the particles flying along a tangential trajectory have to penetrate the thickest layer of the atmosphere. Meanwhile, our journey across the expanses of Io will continue in a northwestern direction. After crossing the boundaries of the Pele sedimentary ring, we will soon see the vast range Boisoli Montes. Its total diameter is about 540 kilometers, and among other peaks, the giant peak called South Boisoli Mons stands out. Measuring 145 by 159 kilometers at its base, this mountain rises more than 18 kilometers above the average level of the satellite, twice as high as the Earth's Mount Everest. The total area of the entire elevation is almost 18,000 square kilometers, which is comparable to the size of a small European country, such as Montenegro or Slovenia. The appearance and structure of this relief feature suggest that it appeared as a result of a tremendous tectonic cataclysm. Probably in the distant past, a fragment of the satellite's forming lithosphere tilted and partially sank into the mantle, while one of its edges remained forever elevated above the surface. As a result, the southeastern slope of the mountain is a steep precipice, about 15 kilometers high, making it one of the highest ledges in the entire solar system. Such formations are impossible on Earth due to higher gravity, and on other planets and satellites due to low tectonic activity. For this reason, South Boisoli Montes can be considered a truly unique peak in the solar system. Moving on in a northwesterly direction, we will soon reach a gigantic chasm called Loki Patra. This formation is the largest volcanic depression on Io, with a diameter measuring roughly 250 kilometers. Thus, the total area of this great chasm exceeds 50,000 square kilometers, which is about 1.5 times larger than that of Lake Baikal, one of the most majestic lakes on our planet. However, unlike terrestrial bodies of water, this chasm is filled with hot sulfur silicate lava. Several dozens of kilometers down from the surface, this lava lake communicates directly with the mantle, which serves as an inexhaustible source of molten matter for it. In the calm state, the temperature of the Patra's surface varies from 270 to 313 Kelvin, which corresponds to the range from 3 degrees below zero to 57 degrees Celsius above zero. Such a low value is due to the fact that the upper lava layers are cooled by contact with Io's rarefied atmosphere. As a consequence, they gradually solidify, forming a slowly growing hard crust, the mass of which reaches a critical value within 400 to 600 days. It then cracks under its own weight and sinks, causing waves of flooding that slam into the surface of the lake at a rate of about 1 kilometer per day. Gradually, the lava lake calms down and begins to be covered with a slowly solidifying solid layer again, until the next flooding cycle. Since water and carbon dioxide, crucial for supporting life as we know it, are practically non-existent on the surface of Io, this celestial body is considered unfavorable for biogenesis. However, the conditions on the surface of Loki-Patra and other lava lakes, hypothetically, may be suitable for the origin of unusual life, resistant to high temperatures and obtaining energy from chemical reactions involving sulfur or iron. There are such creatures on Earth as well, that mostly live in the vents of underwater volcanoes or isolated oceanic caves. Still, due to Io's tectonic activity and extreme temperature variations on its surface, realistically, the probability of this phenomenon is rather low. Interestingly, it may be observed that although the uplands and volcanoes are the most remarkable features of Io's relief, they occupy a relatively small area. Tectonically active areas of the surface are separated by vast and relatively flat regions covered by a thick layer of sulfurous sediments. When viewed from space, these areas stand out with lighter colors, and the largest of them extend for thousands of kilometers. For example, if we head west from the Patra Loki, passing numerous small volcanoes and lava flows, we will soon reach an area called Media Regio. It is a bright and relatively smooth, irregularly shaped area surrounded by mountains and large paterae. Its diameter is variously estimated to be about 2,600 kilometers, and its area accounts for about 12.6% of the satellite's total surface. While most of this region is uniform and smooth, in some places the plain is cut by lava flows associated with adjacent volcanoes. It is assumed that the lithosphere beneath Media Regio has an exceptional thickness, forming something reminiscent of the Earth's continents. That is the reason why such a large surface area has retained its integrity for a very long time. According to another hypothesis, the upper layers of the satellite's mantle are melted in fragments, and there is no liquid magma beneath the tectonically inactive plains. Observations show that in contrast to the volcanic regions, the plains of Io are characterized by a cold climate. Thus, the temperature of Media Regio differs slightly from the average of the entire satellite and is only 110 Kelvin or 163 degrees Celsius below zero. That is hundreds of degrees colder than in most of the volcanic paterae. At this temperature, sulfur dioxide with atmospheric emissions settles as frost on the satellite's surface, forming a flat and smooth relief, colored in hundreds of shades of yellow, red, and black. Whatever is the case, future research will surely yield much more data about this region. Having covered the smooth relief of the sulfurous hills of Media towards northwest, we will see another large chasm, known as Amirani. Just like most of the satellite's volcanoes, it is a lava-filled drift in the crust of the celestial body. Its diameter at its widest point reaches only 37 kilometers, but when viewed from space, this volcano is almost as prominent as the largest features of relief on Io's surface. The reason why it produces such an impression is that Amirani is surrounded by several giant flows of solidified lava. With their dark color against the background of the light-colored plains around, they produce a stark contrast with their brightness. The largest of these flows extends northwards for more than 300 kilometers and is up to 60 kilometers wide. Thus, this feature is the largest active lava flow in the solar system. The second largest lava flow extends westwards for as much as about 250 kilometers. Previously, it was considered an independent formation, but more detailed images of the surface showed that this object is also part of Almorani. In addition, to the east of the main Petra, there is a crown of small dark streams, the color of which suggests that they consist of silicates, which first melted and later solidified. Almorani has a complex internal structure. It is assumed that in addition to the main active area, there are magma tubes lying beneath the surface of the satellite in this region. Their occasional outbursts are the cause of eruptions outside the main rift. Observations in the infrared spectrum show that the main Petra is heated to about 1900 Kelvin or 1630 degrees Celsius, and the temperature of individual hot spots surrounding it reaches 1200 Kelvin or 930 degrees Celsius. It is likely that this value is so high due to the fact that directly beneath the volcano there is an upward magma flow, carrying molten matter from the lower mantle layers. There is also evidence suggesting that Almorani is likely a very young shield volcano. Over time, the lava it spews out will form a vast flat shield, hundreds of kilometers in diameter, and it is likely that this volcano will become similar to Olympus Mons on Mars. It is hardly disputable that in spite of its relatively small size, Io exhibits highly anomalous tectonic activity. In fact, because of its low mass, it does not have sufficient reserves of radioactive substances, the decay of which is the source of internal heat for most planets. It is believed that the reason for the abnormal activity of this celestial body is the tidal interaction with Jupiter. Combined with the orbital resonance that keeps Io in a stable orbit, the gas giant's attraction strongly heats up the satellite's interior and deforms its crust, and this causes frequent and powerful eruptions. Combined with low gravity, they become truly spectacular. Giant emissions reach outer space, forming a scattered cloud of particles around the celestial body. Some of them fall back to Io, others are dispersed by Jupiter's magnetic field, bombarding its atmosphere, while others yet settle on other satellites of the gas giant or become part of its rings. And it is these massive emissions that are constantly occurring in a region called Tvashtar Pateri, which is located in the northern part of Io. This region is an area of pronounced volcanic activity with a diameter of about 300 kilometers. This region is reported to contain several volcanic pateri, presumably associated with a single underground lava source. Over the past 3 decades, several powerful and prolonged eruptions have been recorded here. For example, in the years 1999-2000, the height of the eruption reached 385 kilometers, and volcanic fallout covered a surface area with a radius of more than 700 kilometers. In addition, during this eruption, a gigantic amount of sulfur silicate lava spurted out of the Petra and flooded a huge area around. A few years later, in 2006, another large eruption began in the same area, which lasted 530 days, thus becoming the longest cataclysm in the history of observations of Io. This time, the column of emissions rose to 330 kilometers, sending thousands of tons of matter into outer space. Clearly, Tvashtar is a very active region in terms of tectonics, and the study of its emissions will provide a wealth of data on the internal composition and structure of this satellite. It is no exaggeration to say that Io is a unique and very interesting celestial body, still actively studied. In particular, on the 3rd of February 2024, The orbital station Juno flew at an altitude of 1,500 kilometers above the surface of the satellite and beamed back to Earth a lot of high-quality photos. They showed giant chasms in the crust of the celestial body, as well as volcanic plumes and lava flows. It is assumed that in the future, such flights will help to carry out spectral analysis of Io's atmosphere to clarify its composition and parameters. Nevertheless, despite astronomers' interest in this celestial body, no specialized mission is currently scheduled to explore it. The JUICE and Europa Clipper projects focus on Ganymede, Europa and Callisto because of their potential habitability, although NASA specialists did announce working on a mission called IVO at the beginning of the century, which was supposed to focus on Io's volcanoes. It was never realized, for a number of reasons. Saturn's rings do not have a clear-cut border. The width of their visible part is about as much as 280,000 kilometers, although there are thinnest clusters of dust and rarefied gas beyond these borders. These structures' diameter reaches 16 million kilometers, according to some estimates, although they cannot be seen from the Earth on account of their extremely low density. In spite of the impressive dimensions, the total mass of the ring system is quite small by space standards and is estimated at 3 times 10 to the power of 19 kilograms, which is about 2,000 times lighter than the Moon. Solid objects account for only 3% or so of the structure's overall volume, with the rest filled with rarefied gas and cosmic dust. The disk surrounding Saturn is conventionally divided into several large rings. However, a rather powerful optical telescope will reveal each of them to be clearly made up of a large number of thin circles separated by narrow gaps. These gaps form due to the gravitational influence of both the planet itself and its many satellites. Some of them are as much as several hundred kilometers wide. Even though Saturn's disk reflects several times more sunlight than the gas giant itself, some rings are next to impossible to see. For example, the D ring, the closest to the planet, which consists of tiniest water ice crystals and frozen methane. Its upper border is posited to be located 16,500 kilometers above the planet's conventional surface. As for its inner part, the ring has no clear-cut border and gradually fuses with Saturn's atmosphere. Next to it is the brighter and more massive C ring, which is approximately 17,500 kilometers wide. It is comprised of space objects measuring up to 2 meters and which make up just 0.033% of the disk's overall mass. The brightest and most outstanding part of the disk is located further and is designated the B ring. It begins roughly 34,000 kilometers above the surface of the gas giant, and its width reaches 25,000 kilometers. The thickness of the larger part of the ring does not measure over 5 to 10 meters, while its outer part forms a vertical rim towering up to 2.5 kilometers high. The outermost visible ring of Saturn begins 64,000 kilometers above the planet's surface. It is roughly 14,600 kilometers wide, harboring not only comparatively large ice bits of 10 meters and more, but some satellites as well, such as Pan, Daphnis and others. The existence of such large objects may prove the theory of ring formation following the destruction of the ice satellite. Alternatively, they may have formed at a later time as a result of smaller fragments colliding and merging. Beyond this part of the disk, there lie the almost unobservable F, G and D rings, which formed from cosmic dust and rarefied gas. It goes without saying that most of Saturn's large satellites actively interact with the rings. Traveling as far as 179,000 kilometers away to the region of the so-called E ring, the celestial body dubbed Enceladus is to be found. With a diameter measuring just 500 kilometers, it does not qualify as one of the gas giant's largest satellites, but it stands out for other reasons. The point is that Enceladus is one of the few celestial bodies in our system where there are clear manifestations of cryovolcanic activity. Analysis of the observed emissions proves that there is an ocean of liquid water under its surface. Mathematical modeling shows that its temperature measures from 45 degrees Celsius below zero in the upper layers to 0 degrees at the bottom. Due to a high content of dissolved salts and ammonia, the ocean does not freeze over even in sub-zero temperatures, with the icy shield about 2 kilometers thick covering and thermally insulating it. The celestial body's surface temperature is about 75 Kelvin or 198 degrees Celsius below zero. Its atmosphere is extremely rarefied and is 91% water vapor. Other elements making it up are nitrogen, carbon dioxide and methane. Powerful geysers that erupt from time to time through cracks in the icy crust of the satellite regularly supply its atmosphere with chemical elements, but the celestial body's weak gravity is not enough to prevent the atmosphere from floating away. The upper region of the atmosphere is constantly losing some amount of particles that go to sustain the E-ring. On the other hand, Enceladus constantly captures material from the space around it, thus ensuring its peculiar chemical balance. It is known that geyser activity of this celestial object depends on its orbital movement. It is likely that Saturn's tidal forces deform the satellite's icy shield, causing it to crack in multiple places and to erupt. It is also known that the cryogeyser's emissions contain elaborate organic molecules, which may mean that the conditions in the subsurface ocean may hypothetically be favorable for the genesis of biological life. Also, the gas giant's fifth largest and most massive satellite, Tethys, can be seen approximately 300,000 kilometers away from it. It is peculiar for sharing the same orbit with two other celestial objects, Telesto and Calypso. They are located at the so-called stable Lagrange points, with Telesto 60 degrees ahead of the main satellite in its movement along the orbit, while Calypso, on the contrary, lags 60 degrees behind. Unlike the massive spherical Tethys, these celestial bodies are not that large and are irregular in shape. They measure roughly 20 to 30 kilometers in diameter, with their overall mass just several trillion tons, which is modest by space standards. Interestingly, modeling shows that Calypso and Telesto could not have originally formed in the same orbit with a more massive body following it, which means that they arrived to join it at a much later time. As for Tethys, it is a celestial object with a diameter measuring about 1,060 kilometers, made up of mostly water ice, with some rocky impurities in its composition. The most outstanding feature of its relief is the giant impact crater Odysseus. Its diameter measures around 450 kilometers, which is about twice as small as the diameter of Tethys itself. Its depth reaches as far down as 3 kilometers. There is also an easily noticeable chasm of enormous proportions on the satellite's surface, which is called the Ithaca Chasma. It is as long as about 2,000 kilometers. That is about a third of the celestial body's circumference and as much as 100 kilometers wide. As for its depth, it ranges from 3,000 to 5,000 meters, and the bottom is pockmarked with a great number of craters and minor irregularities of the surface. According to one of the theories about it, the Ithaca chasm formed as a result of Tethys's subsurface ocean freezing over. On turning into ice, the water expanded in size and erupted through the satellite's outer crust. Another assumption about the chasm has to do with the Odysseus crater. It is thought that the impact waves traveled across the entire surface of the satellite and caused a powerful resonance around its circumference. As a result, Tethys's crust cracked, forming this incredibly large chasm. Titan is located about 10 astronomical units from the Sun and is outside the habitable zone of our star. It is Saturn's largest satellite, and its orbit lies well outside the Great Rings, at a distance of about 1,200,000 kilometers from the center of the planet. The trajectory of the celestial body is close to circular, and a complete orbit around the gas giant takes a little less than 16 Earth days. Titan's diameter is 5,152 kilometers, which is 5.6% larger than that of Mercury. At the same time, the mass of the celestial body is relatively small at only 1.35 times 10 to the power of 23 kilograms, which is about 40% of Mercury's. Calculations show that the satellite's average density is about 3 times less than that of the Earth, which means it has a completely different chemical composition. According to contemporary concepts, Titan has a massive core at its center, about 3,400 kilometers in diameter and made up of various silicon compounds. It is surrounded by a thick layer of densely packed ice, which is at the bottom of a cold liquid ocean hundreds of kilometers deep. The ocean, in its turn, contains large amounts of dissolved ammonia, methane and various caustic salts, so that its freezing point is markedly lower than that of ordinary water. For this reason, Titan's subsurface ocean remains liquid even in sub-zero temperatures. It is bound by a thick crust around 100 kilometers thick, consisting of a mixture of water ice and methane hydrate. The tidal forces of the nearby Saturn are continuously deforming it, causing massive rifts and fractures. This causes large cryovolcanoes to form, ejecting great quantities of methane, ammonia and water onto the surface of the celestial body. Methane plays about the same role in Titan's atmosphere as water vapor on Earth. The fact is that the average surface temperature of the satellite is only about 94 Kelvin or 179 degrees Celsius below zero, which is slightly below its boiling point. Natural variations in this parameter cause hydrocarbon vapors to condense and precipitate, forming methane seas, lakes and rivers. Titan's atmosphere is composed mainly of hydrogen, which makes up about 98.4% of its volume, while methane accounts for about 1.6%. Due to its extremely low temperature, the satellite's atmosphere remains condensed near its surface, and the ring of the mountains surrounding it is less than 500 meters high. Most of the surface of the celestial body is permanently obscured from our eyes by multi-layered clouds and an orange-yellow tholin haze. This unique weather phenomenon is a fog formed by tiny droplets of liquid methane and dissolved organic matter, which gives Titan its characteristic hue. This haze pervades Titan's surface, absorbing and scattering visible light but transmitting infrared light. This peculiarity leads to an unusual anti-greenhouse effect, which cools the satellite's surface by roughly another 10 degrees. This effect makes Titan difficult to explore, but thanks to the Cassini's orbiter's infrared cameras, Titan was in parts mapped out earlier this century. Of course, it is not as accurate as we would prefer, but even this much is enough to outline the most striking features of the celestial body's surface. The face of Saturn's largest moon is full of contrasting spots. Some of these reflect most of the light that falls on them, while others are relatively dark in color. One such area is slightly south of the equator and is called Aztlan. One of Titan's highest mountains, Mount Doom or Doom Mons, is located here, towering about 1.5 kilometers above the surrounding plains. The whole mountain reaches up to 60 kilometers in diameter. Its summits are craters, and its slopes have relatively fresh traces of turbulent flows. This may suggest that Doom Mons is an active cryovolcano. To the northeast from it is Titan's deepest depression, called Sotra-Patra. It is a giant depression about 30 kilometers long, the bottom of which is located about 2 kilometers below the adjacent plains. It is thought to be the mouth of a huge cryovolcano, and is part of a single tectonic structure along with Doom Mons located close by. To the north of Doom Mons, there stretches the immense Mahini Fluctus, a vast area covered by Du Mons' ejections. The area extends for about 180 kilometers and varies in width from 15 kilometers in the south to 60 kilometers in the north, where torrents of frozen material alternate with expansive fields of sand dunes consisting of a mixture of frozen methane and water ice. Our flight will continue over the dark area of Fensel. The largest impact crater of the celestial body, Minerva, is located in its northwestern part. It reaches 440 kilometers in diameter, which is about 3 times larger than any other crater on Titan. The depression is about 200 meters deep, and the ring of the mountains surrounding it is less than 500 meters high. The fact is that according to studies, Minerva is not only the largest, but also the oldest extant crater on Titan. Different estimates put the age of the crater at between 300 million and 1.2 billion years. Erosion and tectonic processes have severely damaged the crater, and it is only thanks to its sheer size that it is still visible. Minerva has a well-defined internal structure. At its center there is a small flat plain, surrounded by a ring of hills. This region, with a total diameter of about 200 kilometers, is rather light and clearly visible from space. It is surrounded by a so-called moat, a stretch of dark plains about 50 kilometers wide. This is followed by a ring of low mountains that form the outer boundary of the crater. Our flight next takes us to the south. Here is one of Titan's most impressive and mysterious landmarks, Hautei Arcus. This is a unique formation in the solar system and is a bright arc-shaped region about 600 kilometers long. Radar data from Cassini shows that Hautei Arcus is a natural boundary between the Rocky Mountains in the northeast and a wide valley in the northwest. It is also noteworthy that some parts of this area change color from time to time. This phenomenon is thought to be linked to the eruptions of cryovolcanoes, whose emissions cover the surface of the satellite in a thin layer and then flow into a nearby valley or evaporate into the atmosphere. From space, one can clearly see light channels similar to riverbeds running from the mountains of the Hautei Regio to the northwest. This is where Xanadu is located, which is a vast lowland area with highly rugged terrain. Its northwest boundary is formed by Mithrim Montes, which are 3 parallel ridges stretching for about 150 kilometers, with an average height of 1.9 kilometers. Among the peaks of the southern range is the highest peak on Titan, reaching 3,337 meters. Standing on top of it and looking west, you can see a vast dark plain stretching several hundred kilometers in front of you. It is called Shangri-La, and it is thought that this whole area used to be flooded with liquid methane. It is assumed that it may have persisted beneath the topsoil, similar to the Earth's underground water. Most of this region is below average elevation and has a comparatively flat terrain, but lighter hills can be seen in some places. In the past, these may have been islands in the middle of a hydrocarbon sea. To the west of Shangri-La is the bright Adiri upland area, clearly visible against dark regions around it. The area extends for up to 2,500 kilometers and is a veritable network of numerous drainage canals and caves clearly visible in the photographs. These are thought to have been formed by abundant flows of liquid hydrocarbons. To the west of Adiri is the vast dark lowland area of Belette, and to the east, near the border with Shangri-La, is the Huygens landing site, so far the only vehicle that got to touch down on the surface of an object in the outer solar system. The descent probe was part of a science program called Cassini-Huygens. Together with the Cassini automatic probe, it left Earth in 1997 to spend 7 years in interplanetary space. The spacecraft entered the orbit of Saturn only in 2004, and in early 2005, Huygens reached Titan and plunged into its atmosphere towards new discoveries. Cassini, on the other hand, remained in orbit around the gas giant to carry out its part of the research program, as well as to continue serving as a transponder for the lander. The probe spent just under 2.5 hours in the atmosphere, gradually dropping speed using a sophisticated parachute system. Eventually, by the time it touched down on the surface, its speed was 4.4 meters per second. The probe successfully withstood a momentary 15-fold overload and soon went on to collect information. Huygens was equipped with a vast array of scientific instruments, most of which were designed to study different aspects of the satellite's atmosphere. The probe used them to measure the strength and direction of air currents, as well as the electrical conductivity, temperature and composition of the atmosphere. The probe also took photographs and made audio recordings, and on landing, it examined the composition and properties of the ground. The first thing the cameras saw after making contact with the surface was a flat plain, dotted with rounded rocks of various sizes, the shape of which clearly indicated the impact of powerful fluid currents. A special drill was also used to sample the surface, penetrating 15 centimeters into the ground, while multiple sensors measured its density, texture and composition. It turned out that a thin layer of small rounded pebbles lay on a relatively soft but dense substrate, similar in consistency to wet sand or dense snow. Also, methane gas was released during the drilling process. The ground at the Huygens landing site is believed to have been like sea sand, saturated with liquid hydrocarbons. In total, the probe transmitted around 500 megabytes of information to Earth, including 350 photographs. Further careful analysis revealed several unique features of the celestial body related to its atmosphere. For example, it turned out that at an altitude of about 80 kilometers there is a layer of almost complete calm, as if separating Titan's atmosphere into two parts. Neither air currents of the upper atmosphere nor winds of the surface reach this layer. What caused this phenomenon is not yet known. Another feature is that Titan has two ionospheres. The first of these is located at an altitude of about 1,200 kilometers. It is a layer of heightened electrical conductivity with a large concentration of ionized particles. This layer is known to be formed by stellar wind streams and cosmic radiation. The second ionosphere lies much lower, at an altitude of about 60 kilometers, and the reason for its formation is still debatable. Moving northwest from the Adiri area, we reach Titan's largest hydrocarbon reservoir, the Kraken Mare. Its total area reaches 400,000 square kilometers, which is slightly smaller than the Black Sea. Due to the high viscosity of the liquid hydrocarbon mixture, it has not yet been possible to measure the exact depth of the reservoir. It is only known that in most of the area, it is over 200 meters. Another large natural basin, the Ligeia Mare, is located slightly to the north, near Titan's pole. Its diameter reaches 500 kilometers, and its area is about 100,000 square kilometers, which is about 3 times larger than Lake Baikal. The seas are connected to each other by the narrow and long Treves Fretum, 173 kilometers long. Also in the subpolar region, there are many smaller lakes and lagoons filled with liquid methane. In 2014, analysis of earlier images beamed back by Cassini revealed a large bright object on the surface of the Ligeia Mare. On comparing photographs taken at different times, it was established that within a few months the mysterious object had grown to 260 kilometers in diameter to disappear almost instantly without a trace. Several hypotheses have been put forward to explain it. According to one of them, temperature differences lead to a constant stirring of layers of liquid hydrocarbon mixture in the Lygeum air. This causes nitrogen bubbles to form and rise to the surface from the depths of the reservoir, and thus form large clusters of persistent shiny foam. Due to the high viscosity of the hydrocarbons, such bubbles can reach 4.5 centimeters in diameter and remain stable for months. From space, these structures resemble large islands because they reflect infrared radiation well. Such bubbles would have been a significant hindrance to the operation of a submersible probe, which was scheduled to be launched to Titan back in 2010. However, the mission was postponed indefinitely for various reasons. A higher priority was given to the Dragonfly program, which NASA is working on now. The vehicle is currently in the design phase and has just recently passed key tests of its blades. The launch from Earth is scheduled for 2027. As conceived by its creators, Dragonfly will be an octocopter, an aircraft with 4 twin propellers. This design will allow it to stay in the air even if it loses several blades, unlike its predecessor, the Ingenuity Mars helicopter. A radioisotope thermogenerator, powerful enough to enable the vehicle to climb to a height of 4 kilometers and travel at a speed of about 36 kilometers per hour, will be used as the power source. The scientific capabilities of the probe are also impressive. It will be equipped with a versatile camera capable of producing both panoramic photographs of the surrounding terrain and macro images of the ground. At the same time, the mass spectrometer will make it possible to determine the chemical composition of atmospheric samples and the internal structure of rocks. Perhaps Dragonfly's data will help us clarify an important question. Do we at least have a chance of encountering primitive life? The possibility of life on Titan remains hotly debated. On the one hand, the extremely low surface temperature, the presence of extremely toxic hydrocyanic acid in the atmosphere, and the absence of liquid water would likely rule out the presence of biological life as we know it. Titan's atmosphere, on the other hand, exhibits an incredible diversity of organic compounds. Nitrogenous bases and amino acids, which are the building blocks of proteins, RNA and DNA, could be naturally synthesized on its surface. It is also known that liquid methane can serve as a solvent and potentially play the role of water in biochemical reactions. In addition, experiments show that under certain conditions, a mixture of liquid hydrocarbons with phosphine forms an environment similar to the primordial soup of the early Earth. This means there's a chance of encountering downright exotic forms of life on the surface of the satellite. Pluto is about 40 astronomical units away from the Sun and is a dark and indistinguishable object. This distant celestial body follows a rather elongated orbit around the center of the solar system, completing it every 248 Earth years. We know that Pluto's radius is 1,188 kilometers, which means that it is noticeably inferior in size not only to all the planets of the solar system, but also to some of their satellites, including the Moon. At the same time, observations of the celestial body's proper motion made it possible to calculate its mass with a high degree of accuracy. It turned out to be small, only 1.3 times 10 to the power of 22 kilograms, or 18% of the lunar mass. It is easy to see that Pluto is much more similar to small celestial bodies such as Eris, Ceres or Sedna in terms of its characteristics. This is the reason why it topped the list of dwarf planets in 2006. Due to its long and elongated trajectory, Pluto has a long orbital cycle. Only in 1989 did the planetoid first pass its orbit perihelion since its discovery, approaching the Sun as close as 29.7 astronomical units. Since then, this distance has been continuously increasing and will reach its greatest value in the year 2113. By that time, the dwarf planet will be near its aphelion, which is 49.3 astronomical units away from the center of our system. Thus, Pluto is a very distant and dim space object. That is the reason why it cannot be seen from Earth with the naked eye. And even in images from the Hubble Space Telescope, the dwarf planet looks like a murky brown disk without any surface details. Of course, in such conditions, it is almost impossible to study the celestial body properly. To solve this problem, the New Horizons Unmanned Orbital Station was sent to Pluto in 2006. It took a long 9.5 years to reach its destination. On its way, it beamed back to us detailed images of Jupiter. It wasn't until 2015 that the spacecraft finally reached the main object of its mission. As it flew past Pluto, the station made about 400 observations, collecting more than 6 gigabytes of information, and it took more than a year to transmit this large amount of data to Earth. Unfortunately, the probe's trajectory did not allow photographing the entire surface of the dwarf planet. The fact is that New Horizons did not enter into an orbit around Pluto, but circled round Pluto in order to be able to explore other space objects. Before moving on to the celestial body's terrain features, we need to understand its internal structure. According to the currently accepted model, Pluto has a massive core with a diameter of about 1,700 kilometers, consisting of a mixture of various forms of water ice and rocks in its center. It is surrounded by a 300-kilometer ice mantle. There are probably tectonic processes running in the mantle, and in the moment they are quite understudied. The mantle, in its turn, is covered by a crust, which is a mixture of crystallized gases such as nitrogen, methane and carbon monoxide. According to some assumptions, Pluto's core may generate enough heat to melt some of the icy mantle. In this case, deep beneath the surface of the planetoid, there should hide a very salty and toxic ocean containing large amounts of dissolved ammonia. As for the surface temperature of the dwarf planet, it is very low and is not over 60 Kelvin or 213 degrees Celsius below zero. Our journey around Pluto will start at the most outstanding and well-studied feature of its relief, Tombaugh Regio. This vast area is located in the equatorial zone of the planetoid and is shaped like a heart sketch. This resemblance earned the region its informal nickname, the Heart. Its size reaches 2,300 kilometers, which means that the plane occupies about a quarter of the celestial body's entire area. Tombaugh Regio's surface is not homogeneous. Thus, there is a smooth and light plain in its western part, known as Sputnik Planitia, whose diameter measures 1,492 kilometers. An elevation map will reveal this region to be a vast lowland area. It is covered with a thick layer of nitrogen ice, as well as carbon monoxide and solid methane. These substances have a light coloring, which makes some parts of the plane reflect up to 90% of the light falling on them. There are also virtually no craters, which means that the region is very young in geological terms. According to the main hypothesis, Sputnik Planitia formed about 100 million years ago, when Pluto experienced a collision with a large celestial body. As a result, a huge impact crater appeared. It was filled with contents of the hypothetical inner ocean of the dwarf planet, which rapidly froze there. Some typical features of the relief of the plane can serve as evidence of this. For example, there are quite a number of smooth surface areas on it, ranging from 20 to 30 kilometers in size, with hills and depressions concentrated on the borders between them. This kind of structure resembles convection cells, which appear in any fluid heated from below. This may serve as an indirect confirmation of the hypothesis of Pluto's warm interior. Tombaugh Regio is surrounded by comparatively high mountain ridges. Thus, Hillary Montes, lying to the west from Sputnik Planitia, reach 3.5 kilometers in height. Tenzing Montes are located in the southern part of the heart. Some of them tower as high as over 6 kilometers above the dwarf planet's average surface level. which makes this ridge the tallest one found on Pluto. Remarkably, these rocks are likely to be made up mostly of water ice. And in temperatures as low as here on Pluto, water ice is as solid as rock. Moving a little further south, we can see a deep basin surrounded by massive multi-layered ridges of ice and rock. It is assumed that it may be the vent of an ancient cryovolcano, and the rock around it is its numerous frozen eruptions. Their chemical composition is of great interest to science, because once it is known, the peculiarities of Pluto's inner makeup may be studied. The eastern part of Tombaugh Regio is darker. In addition, its surface is pockmarked with a great number of craters, which means that this region is by far older than Sputnik Planitia. Moving further east along the equator, we will see a chain of dark spots, hundreds of kilometers in diameter. These objects are called maculas and are named after dark deities of various cultures. For example, one of them is named Balrog. Together they form a giant structure called the brass knuckles, encompassing the celestial body along the equator. The maculas are separated by high mountain ranges, and their surface is cut by deep crevices reaching hundreds of kilometers in length. Cthulhu Macula stretches to the west from Tombaugh Regio. It is the largest dark spot on Pluto, measuring almost 3,000 kilometers. Its surface reflects not more than 30% of the light shed on it, which is a stark contrast with the bright and light Sputnik Planitia close by. There is still no reliable information about what maculas are. It is assumed that their dark color is due to a high content of tholins, combined with a relatively large concentration of impact craters. This indicates that maculas are remarkably old. It is also known that the surface of Cthulhu Macula is heterogeneous. Thus, its relief in the western part is undulating. The central part is a smooth plain, and the eastern part is covered with mountains and craters. Leaving the grim spot of Cthulhu Macula behind us, let's head north. Here lies Lowell Regio, the vast valley surrounding Pluto's North Pole. Surprisingly, it is this place that is currently the most illuminated part of the celestial body's surface. The point is that Pluto's axis of rotation has a very large tilt with respect to the plane of its orbit, so in its movement it found itself facing the Sun with its North Pole. It is assumed that it's for this reason that the density of Pluto's atmosphere has tripled over the past 30 years, despite the growing distance from the Sun. It is likely that the Sun's rays evaporate nitrogen ice settled at the pole, which goes into the dwarf planet's atmosphere. In its orbital motion, Pluto has a number of peculiarities compared to the planets of the solar system. In addition to the fact that its orbit has a noticeable tilt to the ecliptic plane, the planetoid itself constantly performs cyclic oscillations near a certain point. This is due to the presence of a large satellite, gravitationally affecting the dwarf planet. It is called Charon, and its mass is 1.52 times 10 to the power of 21 kilograms, which is more than 11% the mass of Pluto itself. As a consequence, both celestial bodies orbit a common mass center between them. They are tidally locked to each other, so they face each other with the same sides at all times. Unlike Pluto's, the surface of its satellite is noticeably darker and shows an abundance of water ice, which is mixed with methane and nitrogen only in some regions. In addition to Charon, there are several other satellites, but all of them are much smaller and are irregular in shape. Nix and Hydra, discovered in 2005, measure several tens of kilometers, and Kerberos and Styx, which were discovered later, are not over 16 kilometers in diameter. All of these celestial bodies consist mainly of water ice, and were probably captured by Pluto's gravity from the Kuiper Belt. Unfortunately, a significant part of Charon was not caught in the field of view of the New Horizons probe's cameras, but many curious terrain features can be found on the visible surface of the celestial body. For example, to the south of the equator, there lies a vast region called Vulcan Planum. Its area is not known precisely, but it is not less than 400,000 square kilometers, which is comparable with the size of an average European country. Here, the highest summit of Charon can be found, Kubrick Mons. Its diameter measures around 40 kilometers, and according to some estimates, its height reaches 4,000 meters. In addition, the mountain is surrounded by a wide circular moat, as it were, up to 2 kilometers deep. According to some assumptions, Kubrick Mons may in fact be a cryovolcano. In this case, it is very likely that the area around it has sunk under its own weight due to the emptying of the underground reservoir. To the north stretches the vast Oz Terra, the surface of which is pockmarked with many craters. It is separated from Vulcan Planum by a system of giant ledges and crevices with a total height of about 1 kilometer. The largest of them is Serenity Kosmo, which is 200 kilometers long, with a width varying from 40 to 50 kilometers. It can be as deep as 7 kilometers, and it is difficult to explore its bottom because of the thick shadows cast by the steep slopes. Further north yet, near the very pole, there is the giant Mordor macula. Its diameter reaches 475 kilometers, and its origin is still debatable. According to the dominant hypothesis today, nitrogen and methane floating from Pluto's atmosphere were trapped by Charon's gravity and so settled at its poles. After exposure to ultraviolet radiation, they turned into tholins and gradually concentrated in the ice of the celestial body. This assumption needs verification, which will be an object of future missions. Charon largely remains a mystery to us because its research is only just starting. Although the Pluto-Charon system is undoubtedly one of the most interesting structures in the solar system, it is still understudied. Unfortunately, the New Horizons probe left its environs long ago, and the celestial bodies themselves are rapidly moving away from us, taking their secrets along. At the moment, the probe is more than 50 astronomical units away from the Earth, and from time to time beams back to us some extremely important data. By about 2030, all of its systems will eventually fail, and the probe will be left all alone in the chilling recesses of space. The solar system is a tremendous cosmic structure, held together by invisible threads of gravity. The star shining at its center provides heat and light not only to the 8 planets, but also to countless other bodies. Every year, dozens of planetoids, asteroids and comets are discovered in the impenetrable darkness of the cosmic abyss. However, the Sun is only one object among countless other stars whose systems of satellites are most likely not less developed and extensive. And this means that the process of learning about the universe can be truly endless.